Okay, everybody, this is going to be the chapter 13-14 quiz tips video. I'm going to go through our practice quiz. And if your quiz differs from this one, it's probably just because it's a different year and we modify it a little bit every year. But I just want to go through a couple of well, the whole thing. I'm going to go through the whole practice quiz, give you some tips as we go, and then hopefully you'll be a little bit more successful. So make sure you've done your practice quiz, have it next to you, and just kind of sit back and enjoy, and hopefully everything went well and you can find mistakes if you have any. So first off, we have some definitions. Kinetic theory is the theory that everything is made of particles that are in motion, everything. How they're moving is different. We've talked about that, and we're going to talk about it later in this practice quiz, but they all are moving. All particles are moving, and solids, liquids, gases, everything is made out of moving particles. That's it, okay? Kinetic is moving. Particles make up everything, so kinetic theory, everything is made of moving particles. Okay, part B, atmospheric pressure. Atmospheric pressure, remember, pressure from a gas is based more on the collisions of that gas with a surface. So as gas particles collide with a surface, they create a little force there, that's pressure. Atmosphere is made out of gases, lots of gases, and they are colliding with surfaces. So when you are talking about atmospheric pressure, you're talking about the pressure of those collisions from the gas molecules in the atmosphere with a surface, okay? So it's just the pressure of the atmosphere on a surface caused by the collisions of those gases. Okay, vapor pressure. I want to share my screen here and talk about vapor pressure just a little bit. So this is two containers, and you can see vapor. Remember, we know what vapor is. Vapor is a gas of something that would normally be a liquid at normal temperatures and pressures. So we have liquid A, liquid B. They're enclosed containers. And when you close a liquid in a container, some of those liquid particles are evaporating and filling that space a little bit, and they're creating a pressure because they're creating additional pressure in there because they're colliding with the walls. What this diagram doesn't show is there's probably also other gas particles in there. So for example, if this liquid was water, the air above the water has things like nitrogen and oxygen and carbon dioxide already. But when you cap the container, water that evaporates from that liquid is now stuck in that space, and it's going to create more pressure. So the vapor pressure is the pressure caused by the liquid that has evaporated in that space, okay? And so when we look at liquid B, we can tell it has a higher vapor pressure than liquid A because it has more of its particles evaporated. Now we can look at this in two ways. This could be two different liquids, and liquid B would just be something that evaporates more easily. So it's going to put more into that enclosed space. Or these could be the same liquid, and liquid B here, this would be just at a higher temperature, for example, because liquids evaporate easier at higher temperatures. Okay, so that's vapor pressure. We did talk a little bit about vapor pressure and boiling. When you have an open container like this, there is a vapor pressure. This upward arrow would represent that vapor pressure of those liquid particles as they become gases. They're creating a pressure upwards. And then we have atmospheric pressure, which is all these white particles would be the atmospheric gases, and they are creating pressure on the liquid by colliding with the surface of the liquid. When those two pressures are equal to each other, that's when we end up with boiling in this liquid, okay? So when those two equal, when vapor pressure equals atmospheric pressure, that's when you get boiling, because those particles will not be able to keep, the air particles will not be keeping those liquid particles at bay anymore, and they will just intermix. That's boiling. Okay, barometer. I don't have a picture of a barometer. You have one in your notes packet, but a barometer is just a device used to measure atmospheric pressure. Okay, so we showed you a barometer made with a straw and a flask and a stopper and liquid. That's one kind of barometer, and you could create measurement markings on that straw and get an atmospheric pressure. But barometers are typically much taller, and they have mercury in them, for example. There are other kinds of barometers as well, but barometer is just a device to measure atmospheric pressure, okay? Kinetic energy, again, there's that word kinetic. Kinetic means movement. So kinetic energy is the energy something has because of its motion, okay? We can increase that kinetic energy by heating something up. So more kinetic energy means higher temperature. All right, effusion. I'm going to show you, actually, I'm going to kind of skip around here. I'm not going to necessarily go in order. So I'm going to just go through this little simulation, and we're going to do diffusion first. So I'm just going to pump a little bit of gas. Actually, I'm going to choose this kind of gas, pump a little bit of gas into this container. Now, I pumped it in. It's got some velocity moving sideways because of that pump. But as we watch, these particles eventually are going to be fairly evenly distributed throughout that container. They're just moving from a high concentration to a low concentration. And maybe about now, they're pretty evenly distributed. Obviously, it's not always going to be perfect, but they have spread out now. They've diffused and they've filled that space. They went from high concentration altogether to low concentration spread out. Now I'm going to show that to you again with a different gas. Throw some of those in there. And you can see that this lighter weight gas, this smaller particle gas, diffuses much faster. It got spread out throughout that container a lot quicker than those heavier blue gases did. And so that's going to be something that's key later as well. Okay, so that's diffusion. It's moving from high to low concentration for gas particles. It's just something that happens with their random movement. They will eventually spread out into lower concentration areas. Now I'll go back to effusion, okay? Effusion, we have to create a hole, okay? Every once in a while, a particle is going to hit that hole at the right angle, and it's going to escape the container. That's effusion, and it takes a little while depending on how big those pores are, but you can see that the red ones are going to probably effuse faster than those blue ones. Just because they're moving faster in general, they have more opportunity to hit that gap and escape the container, okay? So effusion is the escape of a gas through a small hole in a container. Okay, compressibility, I'm going to close that off. I'm going to just show you here, I can compress this gas, which means I can make its volume smaller, okay? Now, if we look at what's happening when I do that, the pressure here is going to increase significantly from what it was before, because now my collisions are happening more. But why am I able to make that compress? Well, all this black space in this simulation is supposed to be empty space. There is nothing in between these particles, nothing. So we can force them closer to each other because there's nothing in between them. We can't do that so much with liquids and solids because the particles are already touching. You can't push them closer to each other if they're already touching each other. So compressibility is the ability to push particles closer to each other. Okay, partial pressure. I'm going to just expand this back out, okay? We can see that the total pressure is being measured over here, and it's bouncing up and down because it depends on how recently things have hit the pressure meter in this simulation, okay? But there is a partial pressure created by the red particles, and there is a partial pressure created by those blue particles. Together, added together, you get the whole pressure. So partial pressure is just the portion of a pressure caused by one type of gas. That's all it is. It's just part of a total pressure, and it's caused by one kind of gas. Normal boiling point. I talked to you a little bit about boiling point already. We're going to see some phase diagrams, again, not necessarily on your quiz, but just to talk about these a little bit. When we look at something, well, let me go down a little further, okay? If we look at a phase diagram, remember, we need to know what normal means, okay? Normal means at normal pressure, standard pressure, sea level, at sea level. The pressure at sea level is 1 atmosphere, and if you trace that over in the graph where it's liquid to gas, we know boiling is when a liquid turns into a gas, and the temperature that happens at sea level is 100 degrees Celsius for water. So this is the normal boiling point for water, not because it's 100, but because it happens at that temperature when you're at sea level. Okay, so definitely need to know the word normal means at sea level. And then boiling is liquid to gas. We already know that. Or freezing or melting is solid to liquid. Freezing is liquid to solid. Normal melting point, normal freezing point are going to appear where 1 atmosphere, again, reaches that solid to liquid line. So normal means at sea level, and then you already know what boiling and melting mean, so you don't need to necessarily study those. Okay, Number two, how do particles of a gas behave according to kinetic theory? Well, we can go back to this simulation and we can look at that. I mean, look at these particles. How are they behaving? Can you describe this to me? Okay. Hopefully you're describing that they are in constant motion. They travel in straight paths until they hit something. They can hit each other. They can hit the side of the container, but they're going to travel in straight paths until they hit there. Then they bounce off of those things and move in a different direction, okay? We had 4 parts of this theory in your notes packet in chapter 13.1, okay? We talk about these gas particles as small hard spheres, and they have insignificant volume. They don't have any attractive or repulsive forces, okay? I just talked about their motion, straight, random, but straight until they hit things, okay? Constantly moving. And then when they collide, they carry forward and all the energy is conserved, okay? So one particle might slow down and another particle might speed up when the collision happens, but overall the amount of energy is conserved, okay? This is definitely the description of an ideal gas, but that's what we use for most gases. And it definitely holds true at high temperatures and at low pressures. All right, number 3, define pressure. Well, again, pressure, we already talked about, is the force of collisions of gas particles with a surface. How does altitude affect pressure? Let's go back here. I'm going to show you a picture right here, okay? If we're looking at altitude, we're getting higher and higher. So let's just say this is the ground and this is like the edge of our atmosphere, okay? And there's a lot of debate about where the edge of the atmosphere is because the particles, look at this. I mean, this is a column of gas 1 inch by 1 inch. So this is massively not to scale, by the way. And this column of gas weighs 14.7 pounds. But if you look at the column of gas, it's much more dense towards the ground than it is towards outer space. Now, where does the atmosphere actually end? Like, is this particle up here, is this just a stray particle that happens to be floating away in outer space? Or is it still being held by Earth's gravity and part of the atmosphere? That's a debate. But the point is, this column of gas is miles and miles and miles thick. I mean, if we're looking at 500 kilometers, that's a lot of miles, okay? A lot of sources say our atmosphere is about 60 miles thick, which would be more like down here, okay? 100 kilometers, approximately 100 kilometers, okay? When you have a small container, you don't see this. Gas particles don't hover around the bottom and never go to the top like this. This is miles and miles and miles thick, which means that gravity is being affected here. And that's why there are more particles here than there are up here, okay? So don't ever draw a picture like this when we're talking about just a bottle of gas, okay? But as you move up through the atmosphere, the density of these particles decreases. And so what's happening to pressure? What's the pressure like here compared to here? Well, if we know pressure is collisions, up here we're going to have a much smaller pressure than we are down here. Okay, we have a much smaller pressure up here than we do down here. Way more collisions happening in this high density gas than in this low density gas up here. So I hope that you can put that together. As you go up in altitude, pressure decreases. All right, when does the motion of a particle theoretically stop? This one I don't have an image for, but if you know that you cool things down, they slow down. You should know that the coldest possible temperature is the slowest possible movement. And slowest possible movement is not moving. Coldest possible temperature is 0 Kelvin, absolute 0, okay? Everything stops. Even the electrons theoretically would just stop and they'd collapse into the nucleus, okay? So absolute 0 is your coldest possible temperature, which means 0 kinetic energy, which means 0 movement, okay? And so what happens to volume when that stops? It collapses. Everything, even the atoms collapse. There would theoretically be 0 volume, okay? All right, define pressure. We already did that, sorry. All right, number 5. How does the temperature of a liquid change as it evaporates? Let's go and look at a picture of evaporation. Okay, so here I have a liquid. Those particles are rolling around each other. Some of them are rolling around faster than others, but they're just moving around, right? Occasionally, one of these particles at the surface has enough energy and gets jostled in just the right way that it leaves. That's evaporation. Well, remember, temperature is the average energy of all of the particles. So the average energy of every single one of these particles, that gives you temperature. If that average energy is high, you have a high temperature. If that average energy is low, we have a cold liquid, low temperature, okay? Now, when these high energy particles at the surface leave in evaporation, that leaves lower average energy particles behind. The highest energy particles are escaping, which means that our average energy of what's left behind is lower. And that means it's colder, okay? Lower energy means colder. So how does the temperature of a liquid change as it evaporates? It drops. The liquid down here is getting cooler because these particles have high energy and are leaving the colder, slower particles behind. All right, number 6, how does heating a boiling liquid affect its temperature? Does it increase the temperature, decrease the temperature, or keep a constant temperature, and why? All right, I want to talk about this in a couple of different ways. First off, if we look at this one, if I am boiling a liquid, that means I am changing it from a liquid to a gas. This is a line. It's not a range. It's a line. At this temperature where this little star is, my water is boiling. At sea level, it's 100 degrees Celsius. My water is boiling, okay? If I heat it, if I continue to heat it, I can push more heat into this. The liquid will boil faster if I do that, but the temperature of that boiling liquid will stay at 100 degrees. How do I know that? Well, if it's 101 degrees, just look at the top of my arrow point here. If it's 101 degrees, if we move over, we are now in the yellow zone of this graph. It is all 100% a gas. There is no liquid left at 100 degrees, okay? If we were to cool it, same thing. If we're at 99, it's all liquid. There is no gas. This point right here is where boiling happens. I can continue to heat it. It will boil faster. It will change into a gas faster, but it cannot go above 100 degrees until it is all in a gas form. And I'm going to show you a graph that also talks about that. If I take an ice cube and I start heating it, there's no temperatures here because this is just applying heat. I am pushing heat, okay? My ice cube is solid until the temperature of that ice cube reaches 0 degrees, okay? So I'm talking water at sea level. At 0, it starts melting, but it's going to stay at 0. Even if I'm continuing to heat it, this mixture of liquid and ice is going to stay at 0 degrees Celsius until all of it has melted, and then the temperature will start to increase again, and will increase until I hit 100 degrees Celsius. Now it starts to boil. We've got vaporizing water. It's boiling, okay? And it's still 100 degrees Celsius. I'm continuing to heat it, but it stays at 100 degrees Celsius until we hit all gas. And then once it's all a gas, our temperature can continue to rise again. So heating a boiling liquid does not change its temperature. All it does is it makes that boiling liquid boil faster. All right, next, number 7, what are 3 factors that affect gas pressure in a container? Well, let's go back to this one, okay? 3 factors that affect gas pressure. So right now we're chilling around 6 atmospheres of pressure. How can I change the pressure here, okay? Well, if I make it smaller, my pressure goes up. Why? Well, less room to move around means they collide more often. So the volume of the container affects the pressure. That's 1. All right, now if I take the temperature, let's cool down this substance, okay? So just introduce some ice there. I'm bringing the temperature way down, okay? What happens to the pressure? It drops, okay? It drops because these guys are moving slower. Remember, temperature is speed of particles. Lower temperature, slower particles. They don't collide as much, and that's going to be a lower pressure. Okay, remember, collisions is pressure. All right, let me bring this back up a little bit here. We'll see the pressure rise. What's the 3rd factor that affects pressure? Remember, all these are in the gas laws. If you just look at your gas laws, you can find all of the variables. Well, the 3rd factor is the amount of gas. If I dump a bunch more gas in here, my pressure goes up because I have more stuff in the same space, and it's going to collide more often. All right, How do real and ideal gases compare? We talked about this a little bit, okay? I can cool this thing as cold as I can possibly get it, and I can compress the gas as small as I can possibly make it, and it will still be a gas in this simulation because this is an ideal gas. No matter what I do to it, it will still act like a gas. That's not true of real gases. Eventually, when you cool a gas down enough, it's going to condense and turn into a liquid, okay? These slow moving particles will eventually show their attractions and attach to each other and form a liquid. That's the condensation piece, okay? So circumstances to make a gas behave less than ideally is cold temperatures and high pressures. Put a lot of pressure on it and you're going to force it into that condensation mode. The opposite is true as well. When I make my pressure lower, they can spread out more and act more like gases. And when I heat it, they move faster and they act more like gases. Their attractions aren't going to affect them as much. Okay? So keep that in mind. Ideal gases aren't real. Their particles do have volumes. Their particles do have attractions, and they are going to eventually condense into liquids under the right conditions. Number 9, what is the difference between a flexible and a rigid container for a gas? Well, let's look at a picture. Okay, I've got a rigid container, a closed off rigid container here, and a flask with a stopper. Why is that rigid? Well, its volume cannot change. And I have a syringe that's plugged, okay, gas inside. This is a flexible container. Why is it flexible? Because its volume can change, right? So what characteristics will remain constant and what can change? Well, we just talked about what can change here. Volume can change. But what's constant? Well, the amount of gas is constant because it's sealed off. It's completely closed, okay? Can the pressure of this system change? Well, we could force the pressure to change if we force the volume, but by itself, its pressure will not change. Even if you heat this, if you heat this syringe, it will just expand, okay? Its pressure is going to be constant based on the pressure outside of the container, okay? So the pressure inside is totally reliant on the pressure outside of the container, okay? This one, again, the amount of gas has to stay constant because it's closed. The volume also has to stay constant because it's rigid. But this one, the pressure can change. If I heat this container, the flask, that rigid container, it will have a higher pressure because its constant volume will not allow for the expansion when the particles start moving faster, okay? So the pressure can increase in this one without an external force like a hand pushing in the piston. Temperature right here could change the volume of this container. All right, and then number 10, difference between an open and closed container. So here's an open one, here's a closed one, okay? We just look at these two. Amount of gas in this container absolutely can change. If I heat this container, the particles in it will move faster and they will start leaving, okay? So amount of gas will change. The volume of the gas, well, the volume is, it's open, so it doesn't really have a volume, a set volume. The pressure of the gas cannot change, okay? The pressure of the gas is going to 100% be related to the pressure outside of the container. So the pressure of the gas here cannot change because the gas can either enter or leave as the temperature is changing, okay? And then again, we've just analyzed this one. Amount of gas cannot change, volume cannot change, pressure can change in this one. All right, allotropes. Let's look at some allotropes of carbon. This is a graphic that I just found, a bunch of different allotropes. The ones that we are most familiar with are graphite and diamond. Both of those are pure carbon, okay? So what are allotropes? Well, just look at these. They're solid forms of carbon that have just different ways the atoms are connected, okay? So an allotrope, general definition, is two different forms of the same element in the same physical state. By the way, this is pure elements. This is not carbon dioxide, carbon monoxide. Meh. Those are not allotropes. Those are different molecules, totally different things, okay? Pure carbon, one element can form graphite, which is the sheets of layers of carbon that slide off of each other in your pencil lead, okay? Diamond is this perfectly tetrahedral throughout the whole crystalline structure, beautiful white, clear crystal, and very, very hard substance, right? Those are the two we're most familiar with. These other ones exist as well as many others, but carbon's a really easy one to relate, and it's something that we have experience with, okay? Different structures, different properties, one element, one physical state, just bonded together differently. All right, number 12, if you wanted to inflate a balloon for a long time, what kind of gas would you use? Well, again, if I open this container up a little bit here, okay, I create the opportunity for effusion. And already 3 red particles have left the container. How many blues? There's the first one right there, okay? So which kind of particle is effusing faster? Which one is escaping the hole faster, right? The red ones, the lighter mass molecules, particles, they're moving faster, they're gonna effuse faster, okay? They diffuse faster as well. If you want your balloon to stay inflated, you wanna fill it with a heavy gas because that one won't escape as quickly as the light gas. Okay, number 13, how do particles in a solid move or in a liquid move? We can go back to our picture of these solids, right? All of these particles in any of these allotropes of carbon are stuck in place. They're bonded to the atoms around them, but they still move. Remember, we had 3 types of movement that we talked about when we did our barometer gas demo worksheet, okay? We have vibrational movement, rotational movement, and translational movement. The solid particles have vibrational movement. That's the one we're most familiar with for a solid. Maybe occasionally one of them will get dislodged from its crystalline structure or its amorphous structure, and that will create either some translational or rotational movement. But primarily, vast majority of movement in a solid is just vibrational. In a liquid, if I go back up to this one, it's not moving, but we can kind of imagine these are rolling around each other. And as they're rolling, they're rotating. The primary movement in a liquid is rotational. There is translational movement. Some of those liquid particles are moving from point A to point B within the container, okay? But primarily rotational movement in a liquid. Gas particles are translational movement all the way, okay? They might be rotating as they're flying through space, but they are definitely translating. That is the primary movement for gas particles. And I know that wasn't part of the question, but I just wanted to bring back those 3 words: translational, rotational, vibrational. Number 14, define and describe the triple point in a phase diagram. What exists or occurs when triple point conditions occur? We have a couple of phase diagrams in here. A triple point is where all 3 physical states exist together at those conditions. So at 5.11 atmospheres and negative 56.4 degrees Celsius, this substance, which if I had to guess might be something like carbon dioxide, okay? This substance exists as a solid, a liquid, and a gas. But not only that, all of the phase changes are happening, all of them, not just the ones that you remember their names, right? Condensation is happening at the same time as boiling, at the same time as freezing, at the same time as melting, at the same time as sublimation, at the same time as deposition. All 6 phase changes are happening at those conditions. All of them are happening at the same time, okay? This, the reason why I say I think this is carbon dioxide or something similar is because at normal pressure, 1 atmosphere, this substance exists as a gas in regular temperatures. When you cool it down enough, it turns directly into a solid, okay? It goes gas to solid, deposition. There is no liquid state at normal pressures. We have to increase the pressure significantly by times 5 or more to get into a liquid state, okay? So that's why it's going to be something like carbon dioxide. When we look at water, here's our triple point. Again, melting, freezing, boiling, condensation, sublimation, deposition, all of that is happening at the triple point. All 3 phases exist at the triple point. Number 15, for any gas law, including simple or ideal gas law, what must the temperature units be in? Okay, we show graphs with Celsius all the time, but in gas law equations, it has to be in kelvins. It has to be, because if I change the temperature from 10 degrees Celsius to 20 degrees Celsius, I did not double the amount of energy. The reason I know that is because 0 degrees Celsius is not 0 energy. We can cool things colder than that, okay? So that means that we can't say 10 to 20 Celsius is a doubling of energy. The scale that has 0 as the coldest amount, the coldest temperature, which means 0 energy, is Kelvin. 0 Kelvin is the lowest you can go. That scale, 10 to 20 Kelvin, is doubling the amount of energy. And it also shows you why 10 degrees to 20 degrees Celsius is not a doubling, because that's really only changing from 283 to 293 Kelvin. That is a very small change when we're talking about amount of energy. All right, that is it for the conceptual pieces. Now I'm going to go through just the answers to these mathematical problems, a little bit of hints, discussions. Remember, you have to show your work if you want credit on these, on the quiz, on labs, on homeworks, and absolutely on the practice quiz, because I'm giving you all the answers right here. So number 16, if you read that problem, you should discover that you need P1V1 equals P2V2 as your equation. Your final answer is 3.3 liters when you adjust for the correct sig figs. 17, your equation would be V1 over T1 equals V2 over T2. And when you solve, you get 2.2 liters. 18, P1 over T1 equals P2 over T2. You should end up with 320 Kelvin if you adjusted correctly for sig figs. It's about 324.4 if you weren't paying attention to sig figs, but we round it to 320 to get to 2 sig figs. Remember, on all of these, we just talked about it, temperature has to be in Kelvin, has to be. Number 18 is P1V1 over T1 equals P2V2 over T2, and you're going to end up with 0.24 milliliters. 0.24 milliliters. If you change these to liters, you could get 0.024 liters, that's fine. But on the standard gas laws and the combined gas law, you do not need to change your volume to liters. Only for PIVNERT, our ideal gas law, do you need to have volume in liters. So 0.24 milliliters. Number 20 is a PIVNERT problem. Now this one is also a stoichiometry problem. So we've got a couple of things going on. You're given a volume, a pressure, and a temperature, and they want to know a mass. Well, we can't go straight to mass, but we can go to moles when you have those three things. So that's what you do first. Use PIVNERT, find the moles. Then use your background knowledge from chapters 10 and 12 to convert those moles into grams. And you will end up with 42 grams of helium, 42 grams. About 10.47 moles if you don't round ahead of time, okay? All right, 21, PIVNERT problem, and you get 26 liters. Make sure you're using the R value that matches your pressure unit. Number 22, you get 0.489 or 0.490 moles, depending on how you rounded your temperature when you change it to kelvins, okay? And that one is also just a PIVNERT problem. So 0.490 moles or 0.489 moles. Hopefully you did well. If you have questions on these, please reach out to your teacher. It would be awesome if we could help you before you take your quiz. So that's all from me. Thanks for tuning in, and we'll see you in class.